Hello and welcome to this chemistry lecture series. In this video, we're going to start chapter 17, which is going to focus on alcohols and some other functional groups that relate and react with alcohols like carboxylic acids and esters. We are going to go through the first section of chapter 17 in this video, which is going to cover just the homologous series of alcohols. So we're going to talk a bit about alcohols, the structure, how alcohol families are grouped together. Then in section 2 in the next video, we'll talk about the reactions to make alcohols. So how do we create alcohol, some of which reactions we have seen already. We're going to then move on to the reactions of alcohol. So how do alcohols themselves react to create other functional groups? And then finally, we're going to look at carboxylic acids and how they react and how do they react specifically with alcohols to create esters. But let's jump straight into section 1, which is going to cover the homologous series of the alcohols. Now, when it comes to alcohols, they're very similar to halogenal alkanes in the sense that we can have different classifications of alcohols. And in certain reactions of alcohols, these classifications will make a difference as far as how the alcohol reacts. The classifications we use for alcohols, again, are very similar to the classifications we use with halogenal alkanes and even with our carbocations. And that's to say that alcohols can be either primary, secondary, or tertiary. Now, before we get into that, let's redefine what an alcohol is from back in chapter 14. Alcohols are going to be compounds with a hydroxyl group. Now, remember that the hydroxyl group is different than the hydroxide ion. The hydroxyl group is going to be the OH group when it's attached to an alkyl group, when it's attached to a carbon, essentially. Now, how is this different from the hydroxide ion? The term hydroxide is used to refer to the ionic version of OH. So the OH minus ion, which is essentially an oxygen with 3 lone pairs of electrons and a bond to a hydrogen ion, or a hydrogen atom, which gives that oxygen a negative charge. The hydroxyl group, YL, not IDE, is also used for OH, but it's used for OH when it's a functional group, when that OH is bonded to an R group or a carbon chain. That's when we use the term hydroxyl. So in alcohol, which is the functional group or the type or the family of reactant or compound, has a hydroxyl group, the OH group, in it. And just like halogen alkanes, these alcohols can be either primary, secondary, or tertiary. And those words mean exactly the same thing they mean with halogen alkanes. It's going to be related to what dihydroxyl group is attached to. If the hydroxyl group is bonded to a carbon that only has one alkyl group bonded to it, then we consider that alcohol to be primary. So we can see that here. We can see how in a primary alcohol, the hydroxyl group, which is right here, will be bonded to a carbon that only has one other carbon bonded to it. The other 2 things that are bonded to a carbon are hydrogens. So this right here is an example of a primary alcohol. So this will be, again, because this is in carbon 1, so we have, let me make that a little smaller there. We have carbons 1, 2, 3, 4, 5. This will be known as 1 pent, because there are 5 of them, pent, and, because everything is single bonded, O, because it's an alcohol. So 1 pentanol. The 1 here at the front refers to the alcohol being in carbon 1. We could also name this pentan 1O, and that would also be a correct name. So it's a primary alcohol. A secondary alcohol is going to be 1, let me here change my things. A secondary alcohol is going to have that OH bonded to a carbon that has two alkyl groups or two carbon chains bonded to it. So we can see that here where this hydroxyl group right here, OH, is bonded to a carbon that has not just one carbon chain, but a second carbon chain bonded to it. And we can see that in this alcohol right here, where the OH is bonded to a carbon here that has two other carbons bonded to it, making this secondary. And again, if we name this just for practice, this hydroxyl group, the OH group, is now in carbon 2 instead of carbon 1. Oops. Make it smaller. So this is going to be carbon 2 instead of carbon 1, which means that this is going to be 2 pentanol. Sorry. So it's 2 pentanol or pentanol, either name would be correct. And that's another version of our one version of our secondary alcohol. And then the last type of alcohol, which is tertiary, is one where the hydroxyl group is bonded to a carbon that has 3 alkyl groups bonded to it. So here we can see how our alcohol, our hydroxyl group, is bonded to this carbon, and this carbon has 1, 2, 3 carbon chains bonded to it. So we can see that here where this alcohol OH is bonded to a carbon that has 1, 2, 3 other carbons bonded to it, making it a tertiary alcohol. So again, if we name this, we're now going to have some methyl groups in here. So this will be carbon 1, 2, 3, 4, 5. So this will be carbon 2. So we'll have not just the alcohol, but also the methyl. So we will have, and I'm going to put up here just so it's visible, 2 methyl, 2 pentanol. Because we still have that alcohol on carbon 2, so it's still 2 pentanol, but now we also have a methyl group on carbon 2. So it's 2 methyl, 2 pentanol. So these are the 3 types of alcohols. Just like the halogen alkanes, we can have a primary alcohol, where the OH is bonded to a carbon that has 1 R group or 1 carbon chain bonded to it. A secondary alcohol, where the OH is bonded to a carbon with 2 other carbon chains bonded to it. And a tertiary alcohol, where the OH is bonded to a carbon with 3 R groups or alkyl groups bonded to it. Like here, where this carbon has 1, 2, 3 carbon chains on it. So that's the different types or the orders of the alcohols. Now, alcohols have very special physical properties. And you probably know this because alcohols are a pretty common functional group, or a pretty common type of compound that is used in everyday life. Everything from rubbing alcohol used to treat wounds and whatnot, to ethanol, which is used to clean certain metals and certain types of plastics, and used in PLA and 3D printing cleaning, and then also in beverages that are made through fermentation, which creates ethanol. So alcohols are a very, very common type of chemical used in all sorts of everyday life. Now, alcohols have very high boiling points. Now, when I say high boiling points, we have to take this in the scope of organic chemistry. Most organic compounds have very low boiling points. Most of them are either gases or very volatile liquids. Whereas alcohols have higher boiling points than their other organic counterparts. And this is due to the same thing that water has to thank for its high boiling point: hydrogen bonding. When alcohols are present in organic compounds, when hydroxyl groups are present in organic compounds, that means that there's an OH bond somewhere in that molecule. That OH bond is polar, with the oxygen being partially negative and the hydrogen being partially positive. This is the same OH bond that is found in water. If we think of a water molecule, OH, H, so H2O. If we think of a water molecule, and then we think of an alcohol, the alcohol has the same OH portion as water does. OH, with its two lone pairs, but instead of having another hydrogen, it has an R group. It has a carbon chain attached to it. And that OH still makes that alcohol have hydrogen bonding. So you can almost think of alcohols as organic water, right? It's water with carbons attached to it instead of a hydrogen. The hydrogen bonds created between alcohol molecules, and these are hydrogen bonds that are created between the oxygens of one alcohol and the hydrogens of another, that attraction between the partial negative oxygen and the partial positive hydrogen is what makes the boiling point of alcohols so strong. The hydrogen bonds are going to be harder to break than the London dispersion forces that most nonpolar organic compounds have. And because of that strong hydrogen bond created in alcohols, most alcohols are liquids at room temperature instead of being gases. So they're going to be liquids at room temperature because of their high boiling point created by the hydrogen bonding that the OH groups provides them. So this also makes alcohols polar or somewhat polar, which makes them miscible with water. Alcohols are going to be able to dissolve. Remember, the word miscible in chemistry means that they mix or they dissolve in each other. Let me put that here so we remember. So they mix or dissolve. Although dissolve is probably not a correct term because we are using two liquids. But probably mix is the better term here. So let me take off dissolve. But they mix together. So the reason why they mix together, the reason why water and alcohols can interact with each other is because they both have hydrogen bonding. And that hydrogen bonding is going to be what gives alcohols a lot of their special properties when it comes to physical properties. Everything boils down to our intermolecular forces, which is hydrogen bonding in this case. Now, the bigger sections of the alcohol are going to have London dispersion forces. So we kind of have to, especially with organic compounds in general, segment the molecules. The long carbon chain, and the longer it gets, the worse it's going to be, gives us London dispersion forces and a non-polar portion. Whereas the OH bond in the alcohol, the hydroxyl group, gives us a polar portion, which provides hydrogen bonding with it. So we do have to realize that the longer this chain is, the more non-polar the alcohol becomes. So a small alcohol like ethanol is a lot more polar than a large alcohol like hexanol or decanol, right? Really large, many carbon alcohols. So do keep that in mind when we're talking about the physical properties of alcohols, in that they're going to become more non-polar the larger the carbon chain is. So that's the physical properties. A chemical property that alcohols share is going to be their acidity. So alcohols have acidic hydrogens, so they can behave like acids to a certain extent. The degree of dissociation, however, is very small. That alcohol, that OH group, does have an acidic hydrogen. What does that mean? An acidic hydrogen is a hydrogen that is in a polar bond and can be removed. So we talked about how the ROH bond here in an alcohol is polar, with the oxygen being partially negative and the hydrogen being partially positive. Well, that OH bond, because it's polar, could be broken by an external factor, like a base reacting with this alcohol. In that case, what's going to happen is that the electrons from our bond are going to be given to the oxygen in the alcohol. And I'm going to put the lone pairs here just to show the difference. So their electrons here, when this bond breaks, like in any acidic reaction, the electrons go to the oxygen, giving us our O with its two original lone pairs, and now because the OH bond broke heterolytically, both of the electrons in that bond are going to go to the oxygen, giving us an O minus ion, and then on the other side, the hydrogen plus that gives off. This is what makes it acidic, right? The fact that we're creating hydrogen plus, the hydrogen ion. This, however, this reaction that happens, and we can see here an actual example using ethanol here. Ethanol can get rid of its OH bond and create CH3CH2O minus and the hydrogen ion, acting essentially as an acid. However, this reaction, which is an equilibrium reaction, has the equilibrium lying very far to the left. And like most acids that we're used to thinking about, like sulfuric acid, hydrochloric acid, nitric acid, the alcohols act like very, very weak acids. The extent to which the molecule ionizes in a solvent is going to be very, very far to the left, and therefore not very strong. So whenever this alcohol does lose a hydrogen, we will get what we call the alkoxide ion, which is the ion of an alcohol after it loses its hydrogen, and a hydrogen ion. So how do we name alkoxide ions? We use the name of the parent alcohol, and then we just change that ano ending to oxide. So ethanol becomes ethoxide. If this was propanol, it will be propanoxide. So on, or propoxide, sorry, so on and so forth. So we're gonna grab that alcohol and just change the ano ending to oxide. So ethoxide, propoxide, butoxide, so on and so forth. Now, the equilibrium that is created does lie very, very far to the left. So alcohols are mostly going to exist as their full organic molecule, not as the alkoxide ion, unless something reacts with them and forces this reaction to happen. Because in water, in solution, this equilibrium lies so far to the left, there's very little alkoxide ion in there. The electron donating alkyl groups, and we have discussed before how carbons are electron donating because they have very weak electronegativities, that are bonded to the oxygen, are going to have an effect on how acidic this reaction or these alcohols are going to be. The more carbon there is attached to the OH group, the less stable that alkoxide ion becomes. So the longer the carbon chain, the less stable the alkoxide ion becomes, the more likely hydrogen is going to reattach to the alkoxide ion and become back into the alcohol. What does this mean? This means that the longer the carbon chain, the less acidic the alcohol. So, longer carbon chain means less acidic alcohol. So to give a few examples as far as like ratings go, let's say something like ethanol, which only has 2 carbons, will be more acidic than something like, let's say here, butanol. 4 carbons. So this will be butanol. And butanol will be more acidic than something like hexanol, which has even more of a carbon chain. The electron donating carbon chain, the alkyl groups is what we call them. Remember, alkyl means carbon chain. So the electron-donating carbon chains bonded to that oxygen in the alkoxide ion are going to create, or are going to concentrate the negative charge on the alkoxide ion. The more carbons which are electron-donating there are near this OH group, the more negative that O minus becomes. And the more negative that O minus is, the more likely the hydrogens are going to be attached to it, and the more this equilibrium shifts towards the left, meaning that the alcohol becomes less acidic when this happens. And this is all thanks to the positive inductive effect that we talked about in the last chapter. The positive inductive effect being that effect where the carbon that is bonded to that alkoxide ion it has a very low electronegativity. And so a lot of these electrons are more attracted to the oxygen than they are to the carbon, pushing those electrons farther towards the oxygen, making this more negative. And the more negative that negative electron is, or the negative ion is, the more likely hydrogen is to reattach, the more this equilibrium shifts to the left. So that's the reason behind the acidity of alcohols. Alcohols already have a very low degree of dissociation. They're very, very weak acids. And the longer the carbon chain is, the weaker the acid becomes, the less acidic they become because of the positive inductive effect from those carbon atoms. And that's it. That's our chapter 17, section 1. I will see you all in the next video where we're going to discuss the reactions of different compounds that can create alcohols, like halogen alkanes, like alkenes, so on and so forth. A lot of these reactions we've already seen, but it is important to remind ourselves how do we not only react the functional group we're looking at, in this case alcohols, but how do we create them as well. I will see you all in the next video. Thank you for watching.